Imagine waking up tomorrow to a world where every object you own has suddenly become twice as heavy. You haven't gained weight, but the Earth's gravitational pull has instantly doubled. At 2 Gs, your body is subjected to a crushing load. If you usually weigh 150 pounds, you now feel like a 300-pound person. Simply sitting up in bed becomes a Herculean struggle as your muscles fight a force they weren't built to oppose. The human frame is a precision-engineered structure designed for 1 G. Under a doubled load, the architectural limits of your bones are reached almost immediately. Without time to adapt, your shins and spinal discs are prone to crack and fail under the sheer weight of your own upper body. Even if your bones hold, your muscles likely won't. They lack the raw power to lift your limbs or keep you upright against this new constant pressure. Most of us would simply collapse where we stand. Once you're down, the crisis moves inward. Your internal organs now weigh twice as much, pressing down on your diaphragm. Every breath requires a massive effort just to expand your chest against the increased weight of your own ribcage. We are rigid organisms, perfectly optimized for the world we were born into. When that world becomes twice as heavy, our basic biological structure becomes our primary liability. Since our bones and muscles give out so quickly, it's worth asking if the damage reaches our microscopic building blocks. Are our individual cells being crushed too? Actually, research from high-gravity test flights shows that our red blood cells and immune cells are remarkably tough. They can experience significant gravity shifts without clumping together or taking any structural damage. The real internal threat is the plumbing. Your heart is a pump designed to move fluid vertically against 1 G. In this new world, the heart struggles to push blood up to your brain against twice the downward force. Blood pools in your lower extremities, leading to a rapid drop in blood pressure and an almost immediate loss of consciousness. While our cells survive the pressure just fine, the macro systems we use to deliver their oxygen fail the moment the weight of the fluid exceeds the power of the pump. This failure of the large and rigid isn't unique to humans. It's a mathematical trap that dooms every large animal on the planet. It's governed by the square-cube law. As an animal gets bigger, its strength only grows based on its surface area, but its weight grows much faster, based on its total volume. If you double the size of an object, it becomes 4 times stronger, but 8 times heavier. An elephant is already at the extreme edge of what biology allows in our current gravity. Its legs have evolved into massive tree trunk-like pillars just to handle the thousands of pounds of pressure pushing down on them. If gravity doubles, that architectural balance is shattered. Those massive legs would snap under a doubled mass that their cross-sectional strength simply cannot support. We see this struggle in the tallest humans, too. Robert Wadlow reached nearly 9 feet in height, but the weight of his own frame was so great that he required metal leg braces and a cane just to stay upright. His body had scaled up, but his bone strength couldn't keep pace. Under high gravity, you can't just build thicker bones to solve the problem. Eventually, the support structures themselves become so heavy that they contribute to the collapse. Our cities are built with this same biological flaw. Modern skyscrapers and bridges are essentially elephants made of steel and concrete. Engineers design for dead load, the permanent weight of the building materials themselves. In a long-span bridge, about 75% of its total strength is dedicated just to holding itself up, long before a single car drives across it. When gravity doubles, that dead load doubles too. The bridge is suddenly consumed by its own crushing weight, exceeding the safety limits of the steel and causing the support columns to buckle. History shows us how thin these margins are. The 1907 collapse of the Quebec Bridge happened because the dead load was slightly underestimated during construction. Even a small error in weight calculation was enough to bring down the entire steel structure. Most of our infrastructure is based on compression, stacking heavy things on top of heavy things. In a high-gravity world, that approach creates a cycle of weight that eventually leads to total structural failure. To survive a 2G world, we have to stop trying to fight gravity with more mass. We need a way to build without stacking. We find the solution by looking at the human tendon. Unlike bones, which provide strength by resisting being squashed, tendons provide strength by being pulled. This is a concept called tensegrity. In this model of a knee joint, you can see that the rigid bones never actually touch. Instead, the entire joint is held in place by a network of balanced pulling. The system is stable because every part is being stretched, not squeezed. If we apply this to architecture, we replace heavy supporting walls with high-strength cables. We move the stress away from the center of the building and spread it across a continuous web of tension. Surviving extreme gravity means shifting our entire approach to physics, letting flexible tension take over the work that used to crush our rigid supports. Buckminster Fuller was one of the first to prove this could work at scale. His geodesic domes used a web of tension to create massive, open spaces with a fraction of the weight of a traditional building. This approach uses the building's own doubled weight to pull its supporting cables tight. The heavier the structure gets, the more stable the tension web becomes. Instead of gravity crushing the base, it provides the pull needed to keep the entire frame rigid. A city built for 2 Gs would look remarkably light. It would be a series of suspended modules, held firmly in place by cables that never stop pulling. This engineering evolution effectively flips gravity. Instead of weight pulling buildings into the earth, it is harnessed to keep the structure perfectly upright. While a shift to 2 Gs would shatter the world we know, the physics of tension provides a map to engineer a society that holds together when the pressure is highest.